Okay, I think we can start now. So welcome everyone to this edition of the HR-VPP thematic webinars organized by the Copernicus Land Monitoring Service. My name is Sofia Oteruono, and I will be giving you today's welcome and supporting our colleagues who will be presenting today. So maybe we can go to our next slide to have already a view of what we can expect today. So what we have in the agenda for this webinar, we will start with my welcoming presentation. Then we have an introduction to the HR-VPP product by Bruno, followed by a use case in the exploitation of the HR-VPP product to create crop calendar maps. This will be presented by Casper. And following that, we will have a presentation by Sebastian regarding cropland drought monitoring in 2018 in Saxony, Germany. And at the end, we will have a Q&A session where you will be able to ask any questions that you have regarding all the presentations here today. For the Q&A session, I will explain in a second how we're going to organize that, and maybe we can go to the next slide just for some housekeeping rules. So this webinar is being recorded. I ask that you please follow general webinar courtesy rules to please mute your microphone if you're not speaking, and the presenters will give you the floor as needed during the Q&A session. And in relation to the Q&A session, we ask that you enter your questions for the presenters through Slido. You can enter using the QR code that you can see right now on the screen. And also I've shared on the chat the link, and you can access Slido there as well. Regarding Slido, we will not only be using it for the Q&A session, but also to engage with you and make this webinar a bit more participative. We will also be posting questions for you, the audience there. We will have 3 questions in total. No worries. This is also not a test. This is just for us to get a better understanding of your use of the CLMS products and your needs as well. In fact, you should already see the first question, and I see that people are already answering. So happy to see that, and we will be posting each one of these questions before each one of the presentations. I think we can go then to the next slide. And here is just to give you an overview of this series. As I mentioned, this is a webinar series. We have 5 episodes to this series. 2 of them have already happened. Maybe you have attended this previous webinars, one focusing on droughts and another one on biomass. This one today is focusing on agriculture, specifically on crop calendars. And we have 2 more upcoming webinars, one on biodiversity and another one on urban green applications. You probably have already seen how to register to this webinar, since you can use the same registration form and the same registration site as for the agriculture webinar. In fact, in that site, you can register to each and every one of the webinars in the series. But if you haven't done so and you're interested in one of these topics, you can just go back to that site and register for this, for the upcoming ones. And you can also share the information with anyone you think could be interested. Without much further ado, I give the floor to Bruno for an introduction.
Okay, thanks, Sophia. So also welcome from my side. So I'm Bruno Smes from Vito, and I'm the lead of the consortium who have been developing the Resolution Vegetation Phenology and Productivity service for the European Environment Agency, and more particular, at least, so working together with Ludwig Forslund from EEA on this service. So I will initially just give a very brief overview on what is HR-VPP. I'm aware that probably some of you who are listening now have been seen the same presentation if you have attended one of the previous 2 webinars, but pay attention, because there is one additional slide which you have not seen. So there is it's worthwhile just keeping an eye on the presentation. So so what is HR-VPP? So it's part of the Copernicus Pan-European Land Monitoring Service, or the Copernicus Land Monitoring Service, more particular Pan-European. So we are covering basically the whole EEA 38 countries plus the UK. It's a biophysical parameter. So if you go to the website, you get to the Copernicus Land website, you go to the biophysical parameters here, and it's part of the vegetation. So we do a systematic monitoring of the state and evolution of the land surface. So what is phenology and productivity? So phenology is mainly the development or the timing of the development of the photosynthetic active leaf of the foliage. So this means we monitor different stages of the leaf development, like the bud setting, the leaf growth, when the leaves are unfolding basically, and then the leaf shedding, for instance, when they are going back and falling then on the floor or on the ground. And it's affected, of course, by several external factors. Light, temperature, water is, of course, very important factors to this development. That's the phenology, so that's more the timing. And then we have the productivity, which is an accumulation of the vegetation biomass. So that's the plant growth. And typically, at least, it's measured also as what sometimes is called a gross primary productivity or a net primary productivity. And of course, that's affected at least by the vegetation vigor and health, the biomass itself. So it's kind of the area under the curve, what we more or less measure during the onset and the end of the season. So it's a suite of products. For HR-VPP, so we start from the Sentinel-2 UTM, so the 10 meter pixels basically and tiles which are there. We start from the level 1C, so that's kind of the rather raw data. At least we do some pre-processing step using the regular Send2 core. We have done some additional kind of cloud screening, which is represented in an additional Q flag, which is on top of the regular Sentinel-2 quality flag. And based on that, we have then a couple of models to calculate an NDVI, which is of course a bend ratio, but then also the FAPAR, fraction of absorbed radiation, the leaf area index, the LAI, which are neural network models, and then the plant phenology index, which is a specific index I'll show you in a minute, that we then further use to extract seasonal trajectories. So that's kind of the curve fitting part. And then based on that, we derive the actual phenological productivity phenological and productivity parameters, so the VPP parameters. We provide that in just native resolution, Sentinel-2 grid, as you can see here in the left part, but we also translate that into the European LAI grid, so EPSG 3035 for the experts, both to the 10-kilometer grid, so keeping the native resolution, as well as also moving it into a 100-meter grid to make it compliant also with other products like the Korean land cover, for instance, which is there. So the vegetation indices is delivered daily within 10 to 12 hours, maximum, or let's say around 9 to 10 hours after the Sentinel-2 scene becomes available. And then the seasonal trajectories is 10 daily, provided at a 10 daily interval. And we deliver that in March of every year. So after the full, let's say, year daily inputs are available, as well as together with the vegetation parameters, VPP parameters, and also in March, but they are, of course, delivered then just in one time step, which is the yearly time step. The whole product is calibrated, so we did a lot of calibration. I'm not going into the details, but you see here some reference data sets. So we have initially been developing the product using the GPP from the flux stores, the phenocams, which capture really through cameras, at least the phenological cycle. Ground measurements coming from the PEP 725 network, so that's field observations, as well as some additional data. You see also there a reference below. I think the slides are available anyhow later on the website, so you can refer back to that presentation if you want to get or that publication if you want to know more about the calibration. And we are using now the same kind of data sets also for the validation, just to keep track on the quality of the products. So here you see short an overview of an example, at least on the comparison of what are these different indices. You see on the top the NDVI, so normalized difference vegetation index, the FAPAR LAI at the bottom, and the PPI in the middle. And you see they have their own positive and negative parts, so depending on what you use it for. But you see here, this is just the mean vegetation index across a full tile. And you see here that the plant phenology index is an index which is specifically calculated to capture well at least the phenological cycle. So there you see here that the curve is a little bit nicer compared to the other one. So that's why we have chosen this index based on this calibration phase to derive the seasonal trajectories and the VPP parameters. So here you see the overview then of the different products in a more graphical way. So the black dots are basically the raw indices. So for every capture from the Sentinel-2, at least we calculate at the daily time step at least this vegetation index, so the PPI as well as the other ones. Once that you take all the black dots together, we use a software package from the University of Lund, which is also a collaborator in this project, which is called the TimeSat, at least. And TimeSat does a curve fitting where you see here this yellow dots and the green line coming out. And based on this curve fitting, at least we provide the seasonal trajectory in a regular interval, so at 10 daily times, and that's this yellow dots what you see. And once that curve is there, then based on the calibration, we derive these phonological stages, which you see here, the start of the season, this is the maximum, and this is the end of the season, which are basically dates and values at the end. So this is an example on what is this plant phenology index, so the seasonal trajectory at 10 daily time steps. So you see 2017 at the left top, then 18, and then going down to 19 and 20. You see the season cycle, so every 10 days you see there the values coming up. You see nicely, at least here, this is for a crop field area, and you see here once it's becoming March, you see in 17, 19, and 20, you see higher values, so the redder shades, compared to 2018, which was much lower values, which represent a bit the drought in 2018. We get less productivity, and also the phenological stages at the end are quite different. This is then the overview of all the phenological metrics. So I'm not going to all of them, but you see here you always have a date, start of season, the date and the value, which are attached to that date. You have the end of season, the max part, and then derived from that you can have a number of additional parameters once that you have identified them. What's the length? Also, what's the minimum value? So, for instance, in the winter, so before between let's say the end of season and the next start of season. Also the left, the right slope, the amplitude, and then the productivity values. And like I said already in the beginning, we have a special quality flag, which is taking the scene layer from the Sentinel-2 classification, and then on top we have added a number of additional quality flags. At the bottom part, you see the similar type, but then the similar, let's say, all the parameters, phenological parameters, but then in a graph. And here at the right side, you just see an overview for the different ecosystem types, going from forest, grassland, up to pastures, for instance. And this is then the productivity that you can calculate also per land cover class across your area of interest, just as an example of the application. This is a seasonal start of season date. It's perhaps a bit more difficult to see in this view, but you see at least going uphill. So these are the altitudes, so the meters at least. You see that, of course, the higher you go in altitude, the later the start of season date is, and that you see here in the map, as well as you can see that here in the graph, going from the elevation of 200 meters to 1600 meters, that the start of season date is increasing, which makes sense, of course. I think this is already my last slide as a short introduction. So if you want to know more and you're not fully acquainted yet with the HR-VPP products, we have a lot of additional documentation where we can spend probably a couple of days to explain all of that. So we have the product user manual, which is the good entry point, both for the daily products, vegetation indices, as well as the, let's say, the temporal, the seasonal trajectories in the VPP parameters, so the ones which are calculated at a yearly scale. Once that you go into the user manual and you want to know more explicit on the algorithm itself, then we have an algorithm description document for both, again, the vegetation indices and the seasonal trajectory and VPP parameters that describe all the algorithms in detail. And then we have the validation, which we issued initially for the base processing we did from 70 to 20. And then there is a second document which we are updating each year with just an annex, And we did that for 21 and 22, and we will be doing that in the next couple of months at least, also to complement that with 2023. On access, there are also different access channels, so we will not handle that in this webinar, but you can just use through a human, through the Wikio platform, you can access the products. But there is also, I think, a bit more advanced interfaces to using the machine-to-machine learning, machine-to-machine interface, that you can just access the products directly. And there is also a set of tools available. If you go to the website, you can find all these, the EEA Copernicus Land website, you can find all these links to all the tools, and including also these manuals will provide you some more details on how to use the tools. Then I promised you an additional slide. So this is the one. So since we are currently talking about the agriculture team, at least I want to say also that there will be a new product also upcoming, which is the HRLL crop type layer. So that's also a yearly product, again at 10 meter spatial resolution. It will also be updated frequently, so annual, and the first publication is expected to be there in March, covering 2017 to 2021. And you see at the right side, you see an example for an area somewhere in south of Spain, where you see different crop types which are mapped at least based on the signal. So that's kind of complementary to what we do, because in the VPP, of course, we are not mapping the crop types, but we can provide kind of quality information on the crop types, and because you have the productivity as well as the seasonal trajectories, and that product will also be complemented with some additional expert products which also provide some additional cropping patterns. So this is kind of a complementary product to what we are doing, which is upcoming soon. Then the future prospects. So HR-VPP is a Copernicus service. So this means that we have a continued production. So it's not just a one shot or whatever. So like I said, we are currently doing the 2023 yearly processing. Next year, there will be we will continue processing the daily products in 2024. At the beginning of 25, again, the 24 yearly products will be done, etc. So the service will continue for the next couple of years. But there are a couple of additions which are expected to be done. So there will be some additional products coming to focus additionally on above ground biomass. So not just a productivity kind of index that we have today, but really having a quantitative measure metric, at least to introduce the GPP and the NPP values. And that can also change perhaps a little bit the seasonal trajectories in the VPP metrics, although it should not be a large change. And the intention is also that the Sentinel-2 archive has been reprocessed to a new collection, and that will also be, so a reprocessing will be done of the full time series in the coming years. And of course, the vegetation indices will continue, but currently we have 4 vegetation indices which we provide at a daily basis, and that number will be reduced. That's also based on several inputs from users that we have got on the importance. So that's what I wanted to say as just a very brief introduction. I don't want to spend more time because the focus is really on the use of the products. And I think then, I'd like to give back to Sophia probably for the introducing the next speaker. Yeah.
Yes, before we move on to our next speaker, just to mention that we have posted a new question on Slido for you, the audience. The previous one was, which are your main application domains for which the HR-VPP crop calendar maps could be relevant? Now our question is, which elements of the HR-VPP crop calendar maps would be most important for your applications? And we look forward to seeing your answers. And now we move on to our next presentation for today by Casper.
Okay, thanks, Sophia, for the introduction. I'll share my screen. Okay, so hello everyone. I'm Casper Bonte, working at Vito Remote Sensing. And I've also been involved in the HR-VPP work, especially in the calibration phase of the HR-VPP work, looking to the consistency and the reliability of the phenometrics over cropland and grassland. What I will present you here today is one of the use cases of HR-VPP, in which I will demonstrate the potential of using HR-VPP phenology data to create crop type-specific crop calendar maps. First, an incentive why we have been developing this use case. Crop calendar information is an important input for a lot of agricultural monitoring applications. Like, for example, in the case of crop type classification, these models need to know in which periods of time certain crop types are growing. And if you have some crop calendar information available at regional level, this kind of input can be really valuable for your tool. Furthermore, most of the existing crop calendar data sets like the USDA and the FAO are often based on long-term historical data, and given the more recent changes in temperature and moisture patterns due to climate change, they can become more rapidly outdated, if not frequently updated. Moreover, often they are only based on national statistical data, and especially in countries with a lot of variety in terms of phenological patterns, these are really limitations in using the crop calendar data sets over there. Furthermore, to date, no regularly updated crop type-specific crop calendar dataset is yet publicly available over the European Union based on land surface phenology information. And in this respect, the HR-VPP phenology data can provide the building blocks to create such a frequently updated crop calendar map at the European level, as it provides start of season and end of season information at 10 meter spatial resolution for every year. Therefore, the objective of this use case was to demonstrate in the first place the potential of HR-VPP for creating crop type-specific crop calendar maps at regional level. Furthermore, in the white paper that describes the entire approach of this use case, also the methodological framework is described, which should allow the user to reproduce this entire work based on HR-VPP data. Within this use case, we selected a few prototypes for creating the crop calendar maps and also assessed the outcome of these results by looking to the statistics and related with some current data. And finally, also something about the HR-VPP data itself. HR-VPP data allows up to 2 growing seasons can be defined on an annual basis, but often for a user, it's not always that easy to delineate the main season out of these 2 seasons. And within this work, also some expert rules and rules of thumb are provided that can help in selecting the main season out of these 2 seasons, if there are 2 seasons present. First, a quick recap about the crop calendar definition itself. Crop calendars defines the timing of key phenological stages per crop type, and often in the context of land surface phenology, it means the start of season and the end of season periods of certain crop types. In the case of HR-VPP, the start of season and end of season period are derived based on changing patterns of the PPI, so the plant phenology index. And based on that, the TimeSat software allows to detect start of season and end of season, as you can also see here on the figure in the slide. Like I already mentioned, there are some existing crop calendar products already available, but they are often at national level, which has some clear restrictions if you want to look to some specific phenology patterns in countries that are quite diverse in terms of phenology. Also, they are distributed in graphic formats, which make it more difficult to do some geospatial analysis on it. And also, often they are become rapidly outdated if they are not updated on an annual basis or at least frequently updated. Furthermore, the input for these crop calendar products are often rely on some ground census data, which is often quite uncertain. So also the accuracy is not always that well known for these products. Before I move to the exact methodological approach, I will provide some idea about the input data that was needed to create these crop calendar maps. As we will create crop type specific crop calendar maps, we also need some information about the crop type distribution. So we need to know at which locations certain crop types were cultivated. And for this, we could use 2 data sets. So one of them is the Lucas data set that for 2018 had spread over Europe some information available on the used crop type at different locations. And on the other hand, we had also the land partial identification system data at national level, which defines for a lot of countries within Europe the crop type information at field level. The problem with the use of these data sets is often that the crop type nomenclature is not always that harmonized. So first, an harmonization exercise had to be done to relate to ensure that the crop type labels for both data sets had the same crop type nomenclature. And then finally, to ensure that there is not that much spatial bias in the crop type data sets, we did a certification of the data sets, and this resulted eventually in 76,000 samples covering 31 crop types. And the spread of these corresponding crop type data that you can see here on the slide. So you see it's quite good distributed across Europe. Of course, in the more northern part of Europe, we have less information on crop types available because there the conditions are also not that suitable to cultivate a lot of crops. Then the next important thing is to select at which regional level you will create your crop calendar map. And here you will always have a trade-off between the spatial detail at which you will provide your crop calendar map and then the phenological differences you will notice in your regional level that you select. So in this case, we only focus on the terrestrial biomes of Europe, which are 6 zones. And the reason we selected this one is because biomes reflect the differences in biophysical features, which are the main drivers for phenological differences. So that's the main reasoning why we focus now only on biomes, but of course, this approach can also apply to any spatial level, so even at NUTS level if you want. And here on the map, you see then the different biomes distribution across Europe. And then finally, but not least, also as input data, the HR-VPP dataset is used. So for every location where we know the crop type, the start of season and end of season at the center read of these samples is taken, and only for the year at which we had the crop type information available. And as you can see here on the pie chart, we have, especially for 2018 and 2021, extracted quite some HR-VPP seasonality data. Then I will move on to the method on how we can derive crop calendars out of these data sets. First, important to stress here that we only focus on 3 prototypes. So we selected only 3 main crops out of the data sets to showcase the potential. And we selected there the maize, potatoes, and winter wheat crops as they are usually cultivated across Europe and quite often cultivated in Europe. And then one important thing that should be done before actually the distribution in phenology patterns can be analyzed at biome level is that you first need to detect the main season out of the HR-VPP data, because like I already mentioned, sometimes we have 2 seasonalities detected in 1 year by HR-VPP, so some rules are needed to properly define the main season out of it. And therefore, a rule-based approach has been defined, which is shown here on the right-hand side. So we'll quickly go through this approach. So as input, you have the seasonality data of HR-VPP, which consists of start of season and end of season periods. If you have only 1 season in a certain year, it's quite simple. Then that season can be used as the main season for your crop calendar derivation. But in the other case, when you have 2 seasons, you will have to apply some rules to select which is the proper main season. And for this, we used as backbone the USDA crop calendar datasets to define some rough periods in which we can expect the main seasonality happening of these 3 crops. And we subdivide basically these periods in 2 types of annual crops. One is the winter crop, another one is the spring crop types. And the difference between them is mostly that winter crops are sown in autumn, while spring crops are sown in springtime. So in case of the European context, winter crops are the winter cereals and all the other crops are mainly spring crops. Using that information about the expected period at the start of season or end of season should happen for these winter crop or spring crops, we can label the season of the HR-VPP to one of these classes or none of these classes if they are not matching. And then we have another conditions we need to check because we now have the labeling into winter crop or spring crop, but in some cases can happen that we don't have any of them. So in that case, that sample was discarded from the analysis. And in the case we have only 1 winter crop season remaining or 1 summer crop, spring crop remaining, we selected that one as the main season. And in case we have, for example, 2 spring crops, because sometimes it can happen based on the seasonalities, we take the one with the longest length as the main season. Once we have done that filtering on the main season, we can stratify the crop title set per biome. And then based on that, derive crop type specific crop calendar maps. So now we'll move on to the result itself. So on this slide, you will see the results for maize, which show you the distribution of the start of season and end of season patterns for the main season of maize among the biomes. As you will notice, I will only show it for 4 biomes the results because for 2 biomes we didn't have enough samples available to do this kind of analysis. For what you should know about the histograms itself, you have different parameters listed here on the upper left-hand part of the histogram. The first parameter defines the amount of samples on which this distribution has been based. And then the second parameter defines, tell you something about if there is a second seasonality detected for a maize parcel, how many times of the cases the second season has been determined as the main season, like I already mentioned in the previous slide. And as you will notice for most of the biomes, the second season, if it is present over the HR-VPP data, is the actual main season of maize. So that's already an easy rule of thumb to use if you want to investigate something of seasonality of maize based on the HR-VPP data. You can easily use only the second season if present to do your analysis. The third parameter defines in how many of the cases we have a second seasonality detected by HR-VPP. And the three last parameters just defines information about the statistical distribution. So the average start of season, the median start of season, and the standard deviation of your distribution. And what is interesting to see here is that among the biomes, the difference in start of season and also in end of season is not that pronounced. So in case for the start of season, there's only an 8 days difference based when you, for example, compare the Mediterranean biome with the most northern biome, which is the boreal forest taiga biome. And the same you can see for end of seasons, even the difference become less pronounced. And what's also interesting to see here on this figure is that in case of the Mediterranean biome, we have quite some early start of season locations and also some early end of season locations. It seems there is some heterogeneity still present within this biome. We did a similar exercise for potatoes, but here the differences are more pronounced compared to maize across the biomes. You will notice that the start of season differ even up to 50 days between the most southern part and northern part of Europe, which is already quite big difference. And also the standard deviation is larger compared to maize. So you have more uncertainty in the biomes depending on which start of season and the end of season. And also on the end of season, you see some pronounced differences, but what also could be noticed here is that the differences between the start of season and end of season becomes less pronounced for the end of season, meaning that for the most northern biome, the seasonal length is a little bit shorter there. Then for winter wheat, we did the same exercise, and there the differences are also quite pronounced. So up to 60 days difference between the southern biome, which is the Mediterranean biome, and the northern biome, which is the boreal forest biome. And also what is interesting to see on these figures is that the start of season for all biomes is always in the late winter period or the spring period, while we should expect normally the start of season happening of winter wheat somewhere in autumn, because then the crops are sown. But here it seems to be a limitation of the time-slot algorithm that only after the regrowth, after the dormancy phase, the regrowth there, then the algorithm of times is only able to detect then the start of season. So there is some delay in the detection of start of season there. And also for the end of season, we see some clear differences following the difference we see for the start of season. We also some interesting rule of thumb you can use if you want to investigate the main seasonality of winter wheat. If there is a second season present over the location of your winter wheat, it will never be the main season of winter wheat. And it's also quite logical because winter wheat seasonality happens quite early in the season. Then also something worthwhile to mention is that sometimes you have for certain locations, as you see here in the red boxes, a late end of season, meaning there's some uncertainty in the detection of the end of season by the time-slot algorithm. And that seems to be happening in cases when you have, after the harvest of a winter wheat location, a quick regrowth of any other kind of crop, like for example, vegetables. And in this case, the algorithm is not always that not that good able in distinguishing between these two seasonalities, and that gives this uncertainty in the end of season. Now some more in-depth discussion of these results. So first starting with maize, here on the slide you can see the crop calendar maps for maize. It's subdivided by start of season and end of season, represented in day of the year. And the difference we mainly noticed is that overall the difference between biomes is quite limited. And this can be largely explained by the fact that maize cultivation is preferably to take place during the warmest periods of the year. And for most of the locations in the biomes, it will be in the same period of time. Furthermore, when you compare the start of season periods with the USDA crop calendar maps, for example, you will notice 1 or 2 months delay. But this difference can be largely explained by the fact that USDA is based on sowing dates, while the HR-VPP start of season is based on the vegetation indices change, which will also always take some time after the sowing date. Like I already briefly mentioned, for the Mediterranean biome, we notice some less skewness in the distribution. Investigation, this can be explained by the fact that for some locations in Spain and Portugal, the season onset is much earlier compared to the southern part of France. So still some heterogeneity is present there in the biomes, but still these kind of results are within expectations. When you will compare the end of season period with, for example, USDA, it will be quite good the correspondence will be quite good. Then for potatoes, there the difference was more pronounced, but that can also be explained by the fact that the temperature constraints for growing potatoes is more restrictive compared to maize. For example, for the tuberization of potato, it depends on the temperature, so it should have some minimal temperature, but also it may not be too hot to grow potatoes, which can also explain the fact why in the southern regions of Europe, it will be quite early in the season that this cultivation of potatoes is taking place. For the end of season, we also notice quite some uncertainty in the distribution of this period, which can be also largely explained by the fact that there can exist quite some varieties in potatoes across Europe, and also the seasonal length will vary according to which kind of potato variety is used. So that's the main reason why we see some deviations across the biomes, but also within the biomes. For winter wheat, we noticed there that the start of season periods now match with the regrowth after dormancy of these crops, so not with the growth before dormancy. So that also explains why we have a big delay compared to the sowing period itself. And this regrowth after dormancy will be temperature dependent, explaining also the large differences we see between the northern part of Europe and the southern part of Europe. However, for end of season, we see relatively good fits with the USDA maps when we are comparing these maps. Some conclusions and outlooks we can have about this data. So overall, we can see that the start of season patterns follow the overall patterns in temperature and moisture regimes. So that's quite within expectations. Furthermore, when compared, for example, with USDA datasets, we see a delay of 1 or 2 months compared to the sowing time, except for winter wheat, because there we had a big delay. For end of season, the uncertainty of the period is more, there's more uncertainty, but still related to when the start of season was taking place. But this uncertainty can be related to many environmental factors, like, for example, harvest practices that are taking place. For example, in the case of maize, farmers can decide to ripen the maize for a longer time compared to other farmers. But also the weather conditions during harvest time can be quite important to when harvest is actually happening. And also the variety of your crop will depend, will determine when the end of season or start of season is taking place. But overall, we can say that HR-VPP data has quite some potential to create such maps, such crop calendar maps at any regional level, because we see some clear correspondence with what we expect. Furthermore, these maps have the potential to update on an annual basis or combine data from different years, because we have already for more than 5 years data available within HR-VPP. And even if some European-based crop type datasets becomes available, like Bruno already addressed, it will be more easy to create some crop type specific crop calendar maps based on the combination of both datasets. So that was it from my side on the crop calendars.
Thank you very much, Casper, for this very detailed presentation. And as you mentioned there, if anyone has questions, we will be answering them at the Q&A session at the end of the webinar. If you have any questions, do not hesitate to post them on Slido. You can find the link on the chat. And now we will move on to our next presentation. Casper, you're still sharing your screen. Thank you very much. So next up is Sebastian. The floor is yours whenever you're ready. You are muted. We cannot hear you.
So
there we go. Perfect.
Sorry. Thank you very much for giving me the opportunity to present my results today. My name is Sebastian Goy, and I work as a desk officer at the Saxon State Office for Environment, Agriculture, and Geology. And one of my tasks is to test remote sensing products for their potential usefulness for my agency. And so free products are of course preferred because we don't have the resources to develop, test, and produce our own products on a permanent basis. And the use case is in Central Europe, we had a severe drought in 2018, which I think most of you have known. And it's also affected my federal state. So the use and testing of vegetation phenology and productivity was very suitable for this question. So I would like to start with a few statistics to put the agriculture drought in 2018 into perspective. Seen over the bull year, a plus of more than 2 Kelvin is extremely remarkable. Looking at the average temperature, which was 8.1 degrees Celsius, there were more or a plus of 500 hours of sunshine, and over the whole year, less volume of precipitation. And this is the whole year. So in the vegetation period, the minus was much stronger, as the first look on this statistic show. And the consequence is that there were significant lower yields for the winter cereals, potatoes, corn, and pastures. And this was so strong that the stational institutions felt compelled to make the possibility of aid money available for farmers. So a drought aid program started by the German state in the federal state of Saxony. For Saxony, the volume was around 300 million euro. And in Saxony, it affected circa 310 farms with 150,000 hectares. It's 17% of all registered area we have in 2080. This drought aid don't only happen in Germany. Other countries made some aid possible, such as Poland. This is a short map of Saxony, so you get a view of which area I'm talking. Here in the south is the border to the Czech Republic, in the east Poland, and north and northwest is other Germany federal states. Let me introduce you to my research objectives. The first was the HR-VPP is an unknown product, so I have to generate test if it's suitable for further analysis. So I start at a higher spatial level in the first question, and then I go into detail for the regional differences of the drought effect, if I am able to work it out, and if there are crop-specific differences. And the lowest level is the farm level in question 4. So is the available data useful to explore why some farms have applied for drought aid, and why other farms did this not? So question 1 is Saxony-wide, number 2 and 3, or number 2 is regional, number 3 is crop type specific, and question 4 on the farm level. We have some starting advantage for this analysis. We can use the free Copernicus land monitoring service products like HR-VPP or Korean land cover, which are area-wide available, and we have the availability of the IACS data. This is vector data with detailed field boundaries and crop types information, which is used for the CAP. The free data is important because we have no resources to product themselves, as I said. And but there is a major problem which lies in the short time series which was available at the time of investigation. And this were only 4 years at this point. And one other problem is the crop rotation, because as a rule, the same field cannot be compared between the drought year and the reference year, because they are always planted with a different crop. So it make no sense to compare a corn field in 2070 with, for example, winter wheat field in 2018, which is the same field, but totally different crops. The data sets used, it's always the same 6 tiles, which are required for Saxony. You can see here, always the same over the years, which I get from the Wikio portal. And it's the season 1 product, as you can see here. So you get the main vegetation phase, the main season, and you can avoid catch crops, for example. I use Koinen cover for from the year 2018. As I said, the ILCS data and the drought aid applications. This is no geodata, but you have got information which farm had applied for the drought aid, and you can connect the farm information with the IACS data. But it's only a hint. As a methodology, I would like to present you now. In order to answer the 4 questions mentioned above, it makes sense to divide the workflow into 3 parts. The first part here answers a question about the basic suitability of the product and evaluates it together with the CLC dataset. So you make a VPP mosaic over the years and calculate the zone statistics. The second step is for the questions 2 and 3, you use the crop data, and this is the partner for the zonal statistics from VPP. This product, or for this analysis, you connect it with a drought aid. And the VPP mosaic forms the basis of the subsequent steps. The calculation of the drought consequences per farm is based on the data in the mosaic and in the data collected in step 2 from the crop. So the focus here in step 3 is the statistical calculation. The target value is that we can identify the influence of drought per farm. And this is very tricky, the farm-specific impact calculation, because as I said, you cannot compare the same crop at the same field, but you only have got 4 years. So you have a problem in your data set because you have not enough data. And the so instead you use the differences of the municipal level As I see, as I will show you as this example, in row A is your farm, okay? Maybe Sebastian Gorge and all. You have different crops with have different VPP values, and your crops are on different areas. You calculate if by the area share, because you don't want high productivity crops as a sum. It would be destroy your index. And so you have some areas, some municipalities with higher productivity. I will show you a map in 2 slides, and areas with lower. And for the drought year, you look at your productivity and compare it to the mean of your municipality. And so you get a difference, a plus or a minus, but you don't take the absolute value because you look at the spatial area from your total farm. And in the end, you sum all values up with your area weighted now and get your indicator value. Yes, it's quite complicated, but it's some way to solve the problem that you have short time series connected with crop rotation. And this is your farm value. If you want to look at the baseline, you change the column F value from the farm VPP average for the reference years 2070, 2090, 2020. I will show it you in the results in a figure. If we start with the results, the general testing, if the VPP is suitable, the answer can be answered as affirmative. And you can clearly see a depression in the VPP mean value for available land and pastures. Precisely in the drought year 2080, here are the years. And please note this is a nationwide average based for the green land cover categories. However, there were obviously no counteracting effects, such as a longer vegetation period in the mountains, which could have compensated for the VPP dips in the lowlands. I've got here continuous urban fabric or inland waters as a category which should not be affected. And you see there is no effect in the drought year, but for your available land, so it's a hint that this product VPP can be useful. I will show a map because I spoke about the regional differences, and you can see it here very clearly. It's the VPP means 2080 for winter wheat, and you see the big black border are the counties, and inside the counties are the municipalities, and there are also strong differences between neighboring municipalities. Here you can see in Meissen County or North Saxony County. So there's strong differences, and if my farm have some winter wheat fields in this area and in this, I have to use the baseline of this for the winter wheat fields here and compare not good areas with bad areas. So now you see we entering the regional drought effect in the results. So question 2 and question 3. And I will show it you with these figures. They are very suitable for presenting the results because first you can see that the crop types listed on the left here contain different VPP means. So every one crop type has its specific VPP here in the mean of the years 27, 90, and 20. And on the bottom, you can see here the counties. So it can be shown that these values vary depending on the district. And the VPP data can therefore be used to show both regional and crop type specific differences. Maybe you see it here in the clover grass. There are strong differences between the region, and you can see the feed grass or peas or sugar beets or winter rapeseed. They always have their own area of VPP means. And the chart on the right
Sebastian,
side.
can you try to finish up in 1-2 minutes, couple of minutes, because otherwise I think we are running out of time.
Okay, sorry. On the right side, you can see the percent deviation of VPP 2080, and you see overall crop types and overall areas, they are almost 20 to 30% compared to the reference years loss. And so the effect of the drought in 2080 is clearly visible and can be impressively illustrated. This effect of drought on the values can also be illustrated with a simple example. Here it's grassland, so it's stationary, and here's no crop rotation. And so you can compare the same fields in the Elbe River floodplain or the Ore Mountain crest, which are rich on grassland. And it's very sharply, there is a strong degree between drought year and not a drought year. The factors of derivation in the VPP means here in 2080, you can see here the difference between the farms which applied for drought aid and which did not apply. And over mostly all counties and all crops, the farms which applied for drought aid have a lower value. They're almost 10% weaker in the VPP means as the farms which did not apply for drought aid. And question 4 was a farm level analysis. And you can see on the top right farms which were better in drought year and better in the reference years. And here are in the bottom right, the farms which are worse in the drought year and better in the reference years. In the bottom left, the farms are worse in drought year and worse in the reference year. And in the top left, the farms are better in the drought year, but worse in the reference year. And here on the left side, the farms are without drought aid application. On the right side, with drought aid application. You can see all farms are very bad in the drought year, but there's no equal distribution. There's no difference in the distribution of the scatter plot points. So you cannot see using the VPP values that there is a special group of the farms which applied for drought aid. Discussion. The official statistics are 10 years averages, and we have got only 4 years. So there's a problem. You can't use the VPP data because only a small number of years are available, and the VPP measures the productivity, not the yield. Another problem is when the grain mature quickly, as in 2080, the productivity losses then overestimated the actual yield. This is here. And on the other side, potato, sugar beets are crops where the yield is into the under the soil. So the index can't maybe see the yield working. So the CLC in the discussion, grain land cover is suitable for the overview. We've seen a drastic reduction in the VPP in 2080, but the values are difficult to communicate to stakeholders. No one understands it. They work with yield or something. And the drought effect is not the yield loss. It's a problem. It's suitable for time series analysis, but co-rotation is a problem. Maybe if the time series is longer, this will be not so bad as it now is. And the indicator does not highlight the farms which are particular need of drought aid. So in my conclusion, the reanalysis is possible, and the drought effect is clearly visible at crop scale, at time scale, at farm level, and spatial scale. But there's long waiting for new data sets. The VPP 2021 was released in November 2024. And you need the spatial crop information, which is not freely available. And you cannot reconstructing the need of drought aid, only with remote sensing. So bookkeeping was the application factor at the drought aid program. And this is the paper for your interest. And here my contact information. Thank you.
Thank you very much, Sebastian, for this presentation. And now, since we're quite over time, I would suggest you jump directly to the Q&A session and maybe select a few of the questions that we've received, since we've received quite a lot and we don't want to keep you here forever. If we don't address your question, please feel free to send us an email. I will be sharing the CLMS contact email on the chat, and maybe one of the first questions that we could answer, I think it's directed to Bruno, is are the R and Python download tools available yet? They don't seem to be able to find the information.
Yeah, I can answer a couple of them immediately, which are related to the
Perfect.
access. And for those who need to leave, I mean, we are recording it anyhow, so you can jump to the last piece to get the answers. So on the download tool, so I've put in the chat at least 2 links, at least where you can download the tools, as well as some color maps. But there is we found out, thanks to your question, there is an error in the new CLMS website, because once that you go to the products, you go to the bottom part, there is a documents section or reporting section, and there is an access to, which is called Access Manual Wikio. And that seems to be the old document, because we created a new document which includes also machine-to-machine interfaces, etc. And we have informed already in the meantime the CLMS people at least to update the website with the new document. So that is the first question. The third question I can immediately answer is HR-VPP data available on the CDSE, Copernicus Data Space Ecosystem? Yes, because we are using the Cloudferro backend for that one, which is also the backend for CDSE. So that data is there available. So if you have a virtual machine or whatever in that machine-to-machine access manual, which will be updated now soon, you will find how to access that one. There was another one about how to download the VPP data for specific polygons as shapefiles, so not the AOI, so not the full tile or whatever. Also in that manual, there is an example at least how to do that. So I suggest at least have a look into that, and then if not, then just send a question to the help desk, and then we can take it from there. And then there is a last one on the access. Why download from the map viewer does not work. If you go to the map viewer, at least you first need to log in, at least with your credentials before the actual download button appears, and then you can download it from that part. So that already solves like 4 or 5 questions in one go.
Yes. So efficient. I love this. Next question that actually had a few votes was, what is the difference between, example, end of season date for season 1 and end of season date for season 2? This is a question for Casper.
Yeah, I can try to answer that question. Just the way it works, you have the inputs vegetation initial data, so the PPI in this case. A curve fitting method is applied within time slots. And if you have then 2 seasonalities after this curve fitting, the first seasonality will assign season 1, and the second seasonality you will see there is season 2. So it's just a chronological order on which the seasons are detected by the time slot algorithm. So it will not definitely be that always the first season is the actual main season of, for example, maize or potatoes. It can always be also the second season. So it's just a chronological definition of the seasonal detection from time slot.
Thank you very much for the answer. And we had another question, which was, why do you use 10 days time steps for start of season, for POS and for EOS calculations?
I can very quickly answer that. We are not using the 10 daily time step. As I said in the beginning in my presentation or introduction, at least we are doing a curve fitting across all the dates, at least. It's only the seasonal trajectories which are exported at a 10 daily basis. But the actual, let's say, selection of the start of season, end of season, etc., and the peak of the season dates are really done at a daily level. So they are not directly related to the 10 daily time steps.
Thank you for that. Sebastian, we have a question for you, which is what do you mean by VPP means?
VPP means is depending on the spatial area of question. If I looked at the Copernicus land cover, so the VPP means are the land-wide VPP calculated means for the class which I'm looking for at the CSC. So it's first question, all available land get a VPP value and I calculate the overall mean. For the second question, it's the regional scale. I generally take the mean of the municipality for each crop and each year, or if I will take a baseline against the drought year, I calculate the total mean for the years 70, 90, and 20, and can compare it to the 2018 means. And so you can get very detailed at crop level and spatial level of municipality, which you need to compare because, as I said, you don't have in this short time series the same crop at the same field often enough to make an analysis.
I see there was also a follow-up question for you, Sebastian, on how fragmented is the landscape in your area, and how would green mixed pixel affect your results?
No, this was only as a general question if I can use or if I can see effect of drought. So I only use green for the overview. Fragmented, yes, section is fragmented, but this was not the question. I only want to see, can I see an effect of the drought in the VPP data for the whole land? And the answer was yes, and then I know, okay, if this is possible, I can start with a detailed analysis.
Thank you very much for that. Since we're already almost 15 minutes beyond our time, I think we can maybe close it here. And if we have not addressed your question, as I mentioned, I've shared on the chat our email address. You can contact us and we will provide you with the information. I want to thank all the speakers today for the presentations, and I'm sure all the information that you've shared with us today is very useful for our users and for potential users. And I thank you, the audience, for staying here, even though we're well over time. And I hope to see you in the next edition of the HR-VPP webinars. Looking forward to seeing you again.
Okay, thank you.
Thank you. Bye.
Thank you.